the combined law has the starting pressure and the starting volume over the starting temperature, starting pressure, starting volume over starting temperature, equal to the final pressure, the final volume over the final temperature. It's general layout for the combined gas law. Now, this first question that we have here, this first example, this is a very basic kind of standard question. Now, to look at this, first off, you can tell this is the combined law because you've got two sets of milliliters, two sets of ATMs. This is definitely combined because you've got two sets of data. So you've got two sets of data. Okay, and this means that you're definitely going to be using the combined law. Now, the combined law again is P1 V1 over T1 equals P2 V2 over T2. And you should write these down as you start because you're going to need to know that. We're going to identify what each of these things are. So we can take a look. This thing here, the gas is at this. This is my T1. This is then my V1 because it's connected. And this is my P1, which means this is my V2. This is my P2. And we are looking for T2. So T2 is going to stay unwritten down. So our P1 is 1 ATM. Times our V1 of 300 milliliters over our 273 kelvins, which you can have the degrees or not, either or. That is equal to P2, which is 2 ATM, times our V2, which is 200 milliliters, over our T2, which we don't know what it is, so I'm just going to leave it there as the variable. Pro tip, you can now go, okay, I've got ATMs to ATMs, milliliter to milliliter, so all those units will cancel and match, which means I have Kelvin to what? Kelvin. So right away, you should be able to figure out what your missing unit is, and all the other units will cancel and go away. This allows us to kind of simplify what we've got. So 1 times 300 is 300, because again, we don't care about units anymore, over 273 is equal to 400 over T2. Now at this point what we want to do is we want to cross multiply. Cross multiplying happens whenever you've got what you want on the bottom basically. So if I want T2 on the bottom, it's best to just multiply this together. And that means I will have 300 T2, and that will be equal to the other thing that I multiply, which will be the 400 times 273. So I'll pull my calculator out. I'll do that. 400 times 273. It's going to be a big old number, but that's okay. And that's going to be 109,200. Okay. Right off my calculator. Alright, so we need to get T2 alone. So what we are going to do is we're just going to finish doing our algebra. I'm going to sit here, I'm going to divide both sides by 300. So I'll take this side, divide by 300, this side, divide by 300, and I should be able to get my answer. And my answer is 364. And I found the units earlier as Kelvin, so I put a box around it, and I'm done. Combined law. Typically fairly easy. Notice my trick with the units. That's how you want to do that. Let's take a look at another one. If a gas is compressed by 400 milliliters to 250 milliliters at 1.5 ATM under constant temperature, what was the initial pressure? So first off, we need to figure out what law we are using, and notice here I've got 2 milliliters, and it says it goes from one thing to another, which means again we have got 2 data sets. We've got a beginning and an end, which means this is combined. There's no grams, no mole, so there we go. Yeah, we should say and without gram or mole. So yeah, this is totally combined, which means we're going to do the whole P1V1 over T1 equals P2V2 over T2. Okay, now this has something new to it. It has a constant. You can see it says there is constant, I messed that up, constant temp. What that means is we can just cross out the temperatures then, because you cancel constants. So remember, whenever you have a constant, you just cancel it, cross it right off of what you're working with. So since that's constant temperatures, I just get rid of temperatures, and there we go. Let's identify what I've got here. I've got a gas is compressed from 400 mLs to 250 mLs. So this is my V1, and this is my V2. And it says at 1.5 atm. So it's saying that this V2 is connected. This 250 is connected to the 1.5. So that means this is not P1, this is P2. This is the second pressure. And the question goes, well, what was the starting pressure? So we're looking for P1. So P1 will remain our variable, and it's going to be multiplied by 400 milliliters. This is going to be equal to 1.5 atms times 250 milliliters. I'm going to do my unit trick. I have milliliters on one side, milliliters on the other, so they will cancel, which means my missing unit is atms. So I'll just write that at the bottom so I don't have to worry about my units anymore, because everything else will cancel. It's a nice little shortcut. It's pretty handy. So what I'm going to do then is I'm just going to take both sides and I'm going to divide out the 400. That is where my variable is, because I want my variable to be alone. So the 400 will cancel, and I'm left with my math over 1.5 times 250 divided by 400. And that gets me an answer. If I look at the problem, there are 2 sigdigs in the problem, so I'm going to only want 2 sigdigs in my answer, which means 0, which is a placeholder, 0.94, my 2 sigdigs. And there we go. That's it. This one is a very common combined gas law example. You've got some canceling going on, but other than that, you know, this is plug and play algebra. Our next example looks easy, and that's always something we need to watch out for. I mean, sometimes it is easy, but other times it's not. When we take a look at this, there are a lot of problems. This is a surprisingly hard question. So this here has got a lot of tricks to it. To start with, there is no moles or grams. So this is probably going to be combined at some point. So let's take a look at some of our tricks. There's actually 3 tricks here. Trick number 1 is the grade killer, right there. Celsius is the grade killer, because you think Celsius will work, but it will not. You need to change this to Kelvin. So no Celsius, you need to make it into Kelvin. So I'm going to take my 100 Celsius, and all I have to do is add 273, and that'll give me my Kelvin, my 373 Kelvin. So this here, this is the temperature I'm going to use. Okay, now it says it starts at STP and it's heated to this, so this here is our T2. So it's good to know that that's what we have. So that's trick number 1. Trick number 2 is this term STP. STP means our temperature is going to be 273 K and our pressure is 1 atm. So there are 2 numbers here that are hidden. If you don't know what you're looking for, you would miss it. So when most people see this problem, they only see 1 number, but there's actually 3, because STP translates into those 2 numbers. This, by the way, is our T1 and our P1. So as you can see here, we very much have our P1 V1 over T1 equals P2 V2 over T2. We have our T2, we have our T1, we have our P1, and it's looking for our new pressure, so it's looking for P2. So we have to go, okay, well, what about volume? As you can see, volume is not mentioned at all. I mean, that's a problem, right? I mean, we need volume. I mean, there's volume here and volume here, but you know, there's no volume in the question. So what do? Well, what you do is you triple check it. You check it 3 times. You read the problem again. If a gas at STP is heated 100 degrees Celsius, what is the new pressure? Again, no mention of volume. You break it down, no mention of volume. And then you take a real good look at it. And if you can say, hey, there's still no volume, then you can assume volume is constant. So after the triple check, then you can treat it as a constant, meaning it just does not matter to the problem, so we can cancel it. But you really got to give a good long look at that before you make that jump. Otherwise, you could goof, and you don't want to goof. So let's plug in our numbers. We've got our P1 is 1 atm. Our T1 is 273 kelvins. We do not know what P2 is. That's what we're looking for. And our temperature is 373 kelvins, which, if you recall, we got from converting Celsius. We do our unit trick. Atmosphere over Kelvin equals blank over Kelvin. It means our missing unit is going to be atmosphere. So now we don't have to worry about units. And all we have to do then is we have to multiply both sides by our 373. Times 373, we'll cancel this out, but we have to times by 373 on that side as well. So I've got 1 by 273 times 373 equals, and that's going to give me my answer, which I will set to 3 sig digs based on the problem, which means 1.37 atmospheres is my final answer. And so that is dealing with the combined law.